So we are into Hahn decomposition theorem. Statement is as follows: let gamma be a sign measure on the measurable space xb. So gamma is a sign measure defined on the measurable space xb. Then we can find a positive set say A and a negative set say B such that x is the union of A and B with the intersection of A and B is empty. So this is what we mean by a Hahn decomposition, which is nothing but the decomposition of the set x into the disjoint union of a positive set and a negative set say B, where A intersection B is empty, that is disjoint union. So this is what we mean by Hahn decomposition theorem, that is decomposition of the set x into disjoint union of a positive set and a negative set. Unfortunately, Hahn decomposition is not unique. That is, the decomposition of x into disjoint union of a positive set and a negative set is not unique, and we will come into that into the later part of the theorem, and we will get into the proof. For the first, I will assume that gamma does not take the value plus infinity. So without loss of generality, we assume that gamma does not take the value plus infinity. So having assumed that it does not take plus infinity, I will consider a set say gamma of P, where P is a positive set with respect to the sign measure. So I am considering the set of all gamma of P such that P is a positive set with respect to sign measure. Now I will consider the supremum of that set, and I denote it by say lambda to be the supremum of that set. Now the proof will proceed by the following method, because for the first we will find a positive set say A, and then we will find with the help of the positive set we will find as negative set say B. So this is how the proof will proceed. And to find a positive set A, it is enough to prove that the sign measure of A to be equal to lambda, because it deduces that because as lambda is a supremum of a set where P is a positive set with respect to sign measure, it is enough to prove that gamma of A, which is sign measure of A, to be equal to lambda, and that deduces that A is a positive set. So we will show that sign measure of A equal to lambda, and lambda being supremum of that set where P is a positive set with respect to lambda. Now having this, also observe that clearly this is a non-empty set, because as empty set is a trivial set, and gamma being a sign measure of an empty set is 0, clearly this is a non-empty set. And also you can see that this is greater than or equal to 0. Lambda is greater than or equal to 0 because a positive set is an empty set is a positive set, and empty set being a positive set, we have supremum of this set to be non-negative. So clearly lambda is greater than or equal to 0. Having lambda to be non-negative, I will consider a sequence AI of positive sets. I am considering a sequence AI of positive sets which converges to lambda, which is nothing but limit of AIs as I tends to infinity is nothing but lambda. So I have a sequence of positive sets which converges to lambda, and I will call A to be union of AIs, countable union of AIs, and A being a countable union of positive sets, AIs are positive. So A being a countable union of positive sets, A is a positive set. So I have A to be a positive set, and AIs are converging to lambda. Therefore, sign measure of A should be less than or equal to lambda. Now I have got one side of the inequality. To see the other side, I will consider A minus AI, which is clearly a subset of A. And A minus A being a subset of A, also A minus AI are measurable. And by previous lemma, we know that measurable subset of a positive set is itself positive. So A minus AI being a measurable subset of a positive set A, we have A minus AI to be a positive set. Therefore, sign measure of A minus AI is greater than or equal to 0. 0. Having this to be greater than or equal to 0, I will consider sine measure of A to be equal to sine measure of AI plus sine measure of A minus AI. And clearly this is greater than or equal to sine measure of A. This is greater than or equal to sine measure of AI, and still this is greater than or equal to limit of sine measure of AI, and we know that and AI's are converging to lambda. The limit of this is equal to lambda. So I have got sine measure of A to be greater than or equal to lambda. They call this to be inequality 2. So clearly by inequality 1 and 2 we have sine measure of A to be equal to lambda. So this proves that A is a positive set. Now for the next, with the help of this positive set, we will find a negative set, say B. Next we will find a positive set, say B, by defining it to be x minus A. So I am defining B to be the complement of A, so that I will prove that B is a negative set. We will prove this by showing that B contains no subset of positive measure. So consequently, we will have B to be negative measure. So we will prove B contains no subset of positive measure. Suppose if E is a positive subset of B. Suppose if E is a positive subset of B, let me see what we will see that. So if E is a positive subset of B, then E and A union is also positive, and E union A is a disjoint set having B to be x minus A. So this is a disjoint union, and E being a positive subset, also A being a positive set, union of positive sets is positive. So this is a positive set, and also this is disjoint. So if I consider the sine measure of E union A, then this should be less than lambda. So we have lambda to be greater than sine measure of this, and this being a disjoint union is same as gamma of E plus gamma of A. And let this be gamma of E, and we know that this is lambda, so I am replacing gamma of A by lambda. And to hold inequality, if this inequality should holds good, then we must have sine measure of E to be 0. So having this inequality, we must have sine measure of E to be equal to 0. So if I consider E to be a positive subset of B, then we are arriving at sine measure of E to be 0. So it proves that B does not contains any positive subset of positive measure, and hence B does not contains any subset of positive measure, so that consequently we have B to be a negative set. So we have B to be a negative set. So we have found now X to be the disjoint union of A and B, where A is a positive set and B is a negative set with respect to the sign measure gamma. So this proves the Hahn decomposition of X into the disjoint union of positive sets and a negative set. Coming into the uniqueness part, I said that this decomposition is not unique because I can have a decomposition of X into A union N and union B minus N. Clearly this is a disjoint union where N is a null set, and you want to know that what do you mean by null set. A set is said to be a null set if it is both a positive set and a negative set. So we have X to be the disjoint union of A union positive set union null set and negative set minus null set, and clearly that is a disjoint union having A union N to be positive, B minus N to be a negative set. We have another decomposition of X, so that proves that Hahn decomposition is not unique. Next, as an example to Hahn decomposition theorem, we have if R is a set and M to be a collection of all Lebesgue measurable sets and M to be the Lebesgue measure defined on that, we have R, M to be a measure space. And if I consider A to be the set of all irrationals and B to be set of all rationals, and I and Q are measurable, with R to be the disjoint union of Q and I with their intersection to be empty, it is disjoint union. So we have I to be a positive set with respect to M and Q to be the negative set with respect to M, so that we have the decomposition of R into the disjoint union of a positive set and a negative set. Also, you can have R to be the disjoint union of Z and its complement. So clearly, as Z is countable and countable sets are negative sets, I have this to be negative set and this to be a positive set, and you have another decomposition of R. Next, we have an important definition, and heading to the definition is about mutually singular measures. So let me see what do you mean by a mutually singular measures. Two measures mu and gamma defined on a measurable space are said to be mutually singular, denoted by this symbol. If there are disjoint measurable sets, say A and B, with the set to be the union of A and B, such that measure of A, which is mu of A to be 0 and gamma of B to be 0. Observe that first mu of A is 0 and gamma of B is 0. So two measures, say gamma and mu, are said to be mutually singular, and it is denoted by this symbol. If there are disjoint measurable sets A and B with their union to be equal to the set, such that mu of A is 0 and gamma of B is 0. So this is said to be a mutually singular measure. As an example for a mutually singular measures, if I consider say two measures M and a zero measure 0, so I am considering two measures, one is a Lebesgue measure M and the other is a zero measure, and I will consider a set R, which is a set of all real numbers, and along with that the collection M of Lebesgue measurable sets, so that Rm is a measurable space. So if I define two measures, one is Lebesgue measure and a zero measure on the measurable space Rm, and considering A to be the set of all irrationals and B to be the set of all rationals, as of that I have R to be I union Q, along with that I intersection Q is empty, and observe that again, if you take measure of Q, which is as Q is again countable, we have measure of Q to be 0, and again if I consider zero measure of I, it is 0. So measure of Q is 0 and zero measure of I is 0. So as of we are finding measure of first set and another measure of second set. So measure of first set and another measure of another set. So both are equal to 0. So I can conclude that Lebesgue measure and zero measure are mutually singular measures. So we are into the next theorem, Jordan decomposition theorem. Statement is as follows. Let gamma be a signed measure defined on the measurable space xb. Then there are two mutually singular measures, positive part and negative part, defined on the measurable space, such that gamma can be decomposed into positive part and negative part. So moreover, there is only one such pair of mutually singular measures. That is, the decomposition of the signed measure into positive part and negative part is unique. So we have Hahn decomposition was not unique, but we have Jordan decomposition to be unique. Now let me come again. So if we have gamma to be signed measure on the measurable space xb, then there are two mutually singular measures. You know by now what we mean by a mutually singular measures. Say positive part and negative part defined on the measurable space, such that signed measure is a positive part minus negative part, and such a decomposition is unique. And also note that since gamma is a signed measure, gamma assumes at most one of the values plus infinity or minus infinity. That is the definition. So as gamma assumes at most one of the values plus or minus infinity, we have either of positive part or negative part to be finite. So we must have either of positive part of gamma or negative part of gamma to be finite. So this is what we mean by Jordan decomposition. So coming into the proof, since given that gamma is a signed measure, with the help of Hahn decomposition theorem, I can find a decomposition of x into a and b such that they are disjoint. X is the disjoint union of A and B, where say A is a positive set and let B be a negative set. So this is what we have by Hahn decomposition theorem. Now having this, I will define positive part of gamma to be a mapping from B to 0 infinity, and I will define it by positive part of say E, where E is a measurable set, to be E intersection A. I am defining positive part of E with intersecting it with a positive set A. Similar fashion, I will define negative part of gamma from B to 0 infinity by negative part of E, again where E is a measurable set, by minus of, I am defining it by minus of gamma of E intersection B. So I am defining negative part by minus of gamma of E intersection a negative set B. So now I have gamma plus and gamma minus, which are negative part and positive part of gamma. And before proving the positive part and negative part are mutually singular, and also gamma is same as positive part minus negative part, before proving those two things, mutually singular and the decomposition, first I need to prove these two are well defined measures. So before going to that proof, we need to prove gamma plus and gamma minus, that is positive part and negative part, are well defined measures. So in order to prove those are well defined measures, we need to prove that they are non-negative extended real valued functions. The measure of their empty set is 0, and these two satisfies countably additiveness. So for the first, clearly these two are clearly non-negative extended real valued set functions. It is clear that. So coming into the measure of empty set, if I consider positive part of empty set, clearly by the definition, positive part of a set is E intersection with A. So this is nothing but P intersection with A, and again this is a measure of empty set. And since gamma is a signed measure, again by definition, measure of signed measure of empty set is 0. So I have positive measure of empty set to be 0. So coming into the negative part, if I consider negative part of empty set, and it is defined by minus of E intersection B. So it is minus of P intersection B. So again this is same as minus of empty set, and again this is a signed measure, so we have signed measure of empty set to be 0. So clearly we have it to be 0. So now we are remaining to prove that these two satisfies countable additiveness property. Now we are about to prove that positive part and negative part are satisfying countably additiveness property. For that, I will consider a sequence of sets, say EI of disjoint measurable sets. Disjoint measurable sets. So I am having EI to be sequence of disjoint measurable sets, and I will consider positive part of countable union of EIs. And by definition of positive part, we have this to be same as union of EIs, that is a countable union of EIs intersection with a positive set, say A. And this is same as sign measure of union of, that is countable union of EIs with A. So having this, since sign measure, gamma is a sign measure, we have gamma to be countably additiveness. So this satisfies countable additiveness property since gamma is a sign measure. So this is same as summation of gamma of EI intersection with A. And having this, by definition of positive part, I can write this as summation I from 1 to infinity positive part of EI. By definition of positive part, this is equal to positive part of EI. So we have arrived at summation positive part of EI taking this. So this implies that positive part of gamma is, or sign measure, is satisfying countably additiveness property, and the proof of negative part follows on the same way. So we have proved that the positive part and negative part satisfies countably additiveness, which proves that positive part and negative part are well defined measures. Now we are left to prove that they are mutually singular and the decomposition. So for the first proving the decomposition, if I consider positive part minus negative part of E, which is same as positive part of E minus negative part of E, and by the definition we have this to be E intersection with a positive set, and here it is minus, so the definition this is minus of sign of E intersection with V, so you will be having a plus sign here, so E intersection with a negative set B. By the way, the definition, the negative part is minus of E intersection with B, so we have plus here, and now this is M as sign measure of E intersection A union with E intersection B. So having this, now this is same as sign measure of E intersection with X. So we have got sign measure of E intersection with X, and since E is a subset of that, we have this to be sign measure of E. So we have arrived at the decomposition. So positive part minus negative part is same as the whole of the sign measure. So we have proved the decomposition. The final part to prove that the positive part and negative part are mutually singular. So to prove that positive part is mutually singular with negative part, I will consider positive part of the negative set B. So I am considering a positive part of negative set B, and by definition this is a positive part of sign measure of that set intersection with a positive set, and A is our positive set here. I took positive part of B, and by definition this is the sign measure of this intersecting with a positive set, and A is our positive set. Since these two are disjoint, I have this to be empty, and since this is a sign measure, the measure of empty set is 0. In a similar fashion, if I consider negative part of set A, and this is defined by minus of A intersecting with the negative set, that is B, and again these two are disjoint, we have this to be empty, so we have 0 on the same lines. So we have, and since by the definition we have, if you are taking a measure of one set and another measure of another set, we are arriving at both the measures to be 0, and clearly that implies that positive part and negative part are mutually singular measures, which completes the proof. For the next, we have some note and definitions to follow. To see the note for first, the measure mod of gamma defined by mod of gamma of E to be positive part of E plus negative part of E, then it is called the absolute value of total variation of gamma. So we have defined the modulus of gamma to be the positive part plus negative part, and it is said to be the absolute value of total variation of gamma. Coming to the next definition, it is about absolute continuity of two measures with respect to two measures. A measure gamma is said to be absolutely continuous with respect to the measure, say mu, if gamma of A is 0 for each set A for which mu of A is also 0. So we say a measure gamma is said to be absolutely continuous with respect to another measure, say mu, if gamma of A is 0 for each set A for which also mu of A is 0. And we represent the symbol by this absolutely continuous. We use this symbol to say that gamma is absolutely continuous with respect to mu. And we have some note on regarding absolutely continuous of measures and mutually singular measures. And for the first, in case of signed measures, we have spoke about the normal measures here, mu and gamma are measures. But here, what if mu and gamma are signed measures? So in case of signed measures, mu and gamma, we say that gamma is absolutely continuous with respect to mu if mod of gamma is absolutely continuous with respect to mod of u, and we say gamma is mutually singular to mu if mod of gamma is mutually singular to mod of mu. So that's what we have. And for the second note, also mu is absolutely continuous with respect to that measure itself, and if gamma is some scalar multiple, say constant c, a real constant of u, then gamma is again mutually singular to mu. So if I have gamma to be multiple of a real constant of a measure mu, then we also have gamma to be absolutely continuous with respect to mu. And finally, coming to about zero measure is absolutely continuous with respect to a measure mu, but mu is not absolutely continuous with respect to zero measure for a non-zero measure mu. So if mu is a non-zero measure, then zero is absolutely continuous with respect to mu, but mu is not absolutely continuous with respect to zero measure. Now we have a question that what if mu is a measure defined on a measurable space xb, then what would be another measure gamma such that gamma is absolutely continuous with respect to mu. So the question is, if mu is a measure defined on a measurable space, say xb, then what would be another measure? In general, what can we choose as another measure gamma such that gamma is absolutely continuous with respect to mu? So the answer is, if we can define gamma as a map from b to 0 infinity, and if E is in the sigma algebra B, as B the sigma algebra, and if I take a set E to be in B, then define a map from here to here by, say, gamma of E, as we need to know what should be gamma of E to be integral of f over the set which is in the sigma algebra with respect to mu. So we have already a defined measure mu on xb, so we are defining gamma of E to be integral of f over E with respect to the measure, already known measure mu. So having this, we will show that gamma is absolutely continuous with respect to mu. Before showing gamma is absolutely continuous with respect to mu, we need to show that gamma is a well-defined measure. So in order to prove that, clearly gamma of E is non-negative for the first. So it is obvious gamma of E is non-negative, and also since gamma of empty set is nothing but integral of f over empty set with respect to mu, it is clearly 0. So finally, in order to prove that gamma is countably additive, if I consider a sequence EI of disjoint measurable sets, then I have what gamma of union of EIs, countable union of EIs, to be same as by the definition, it is integral of f over countable union of EIs with respect to mu, and this is same as summation of integral of f over EIs with respect to mu and I running from 1 to infinity. And since this is the definition of gamma of E, I have this to be summation of I from 1 to infinity gamma of EI. So I took gamma of union of EIs and show that it to be equal as summation of gamma of EIs, which proves the absolute continuous of, countable additiveness of gamma. So we have proved that gamma is a measure. Now to see gamma to be absolutely continuous with respect to mu, if I choose measure of E to be 0, then obviously our gamma of E should also be 0, as gamma of E is integral of f over E with respect to mu, and mu measure of E is 0, so we have this to be 0. So if I suppose mu of E is 0, then for each set E I have gamma of E also to be 0, which proves that gamma is absolutely continuous with respect to mu. So in general, if I define a measure mu on xb, then I have gamma to be integral of f over d mu, where again I have to mention this, f is a non-negative measurable function. I forgot to mention at the first. So f is a non-negative measurable function. That should be in mind. So in general, if I need to show that two measures are absolutely continuous, given that already mu is a measure on xb, if I choose gamma to be integral of f over e with respect to mu, where f is a non-negative measurable functions, we have gamma to be measure and gamma is clearly absolutely continuous with respect to mu. But the converse of this is not true. And we will have a clarity of this on the converse with the help of Radon-Nikodym theorem.